Today, we're locking in on a very specific, absolutely crucial goal. We're going to define, explain, and honestly just master proper computing terminology across hardware, software, and communications. My name is Hector Wong, and I profess ICS at Leeward Community College. My office is located at the Waianae Moku Satellite Campus. Come visit. Why? Because we want to equip you to seamlessly interact with other tech professionals and prep you for higher level IT courses. We'll be drawing exclusively on the industry standard curriculum from Professor Messer to get you there. So let's dive right in. We've all heard it, right? Or let's be honest, maybe we've all actually done it. The app froze, so I just held down the power button until the whole thing died. Well, this incredibly common frustration perfectly highlights exactly why tech terminology matters. In the tech world, ambiguity costs time and money. Using precise language bridges that critical gap between merely guessing at a problem and actually effectively fixing it. For instance, instead of crashing the entire system by holding down the power button, knowing the right terminology leads you to a professional approach, like utilizing a specific tool to terminate a single unresponsive process without risking corrupting the whole system. Getting the standardized vocabulary down is literally your very first step to mastering IT. So here is our roadmap. We're going to build our understanding from the bottom up. First, hardware, the tangible foundation. Second, software, the digital brain. And third, communications, how we connect it all to the world. Let's get going. Starting with section 1, hardware, the tangible foundation. Let's kick off our journey right at the physical base of the technology stack, the stuff you can actually touch. Think of the system board, widely known as the motherboard, as the actual spine of your machine. It connects all the other components together, including holding the central processing unit, or CPU, which acts as the true brain of the computer. Now, a quick, super important terminology tip for you. That metal box that sits under a desk, that is the chassis or the case. Please, I beg you, never call that outer shell the CPU or the hard drive. Okay, let's clear up what is easily one of the most common mix-ups in all of computing. Confusing memory with storage. RAM or random access memory is just a temporary volatile workspace for active tasks. Basically, it completely clears out the second the power cuts off. On the flip side, a hard disk drive or solid-state drive provides non-volatile long-term retention. So if someone says they need more memory for their photos, you can gently correct them. What they actually need is long-term storage, like an SSD. They would really only need more RAM if their system was struggling to open 50 of those photos all at the exact same time. So how do all these devices actually hook up? Through peripheral interfaces. Identifying exactly how they connect is crucial because just saying USB really isn't specific enough anymore. You've got to know the difference between the older directional USB Type A and the modern reversible USB Type C. Having this exact vocabulary means you can correctly tell a user that they're trying to jam a reversible Type-C cable into a legacy Type A port instead of just vaguely saying, it doesn't fit. We also use HDMI and DisplayPort for high-fidelity digital video and VGA for those older legacy analog connections. Electronics generate heat. That's just a fact. And managing that heat requires specific hardware, things like a CPU cooling fan, heat sinks, and thermal paste. Here's the big takeaway. If a computer randomly shuts down under a heavy workload, a trained troubleshooter doesn't just throw their hands up and say it broke. No, they know to look for thermal throttling, which means the system is purposely slowing down because it's overheating. Or they might look for a failing power supply unit, the PSU, that isn't properly converting alternating current from the wall into the direct current power the internal parts actually need. You know what happens before your screen even lights up or the operating system loads? The system runs a pause or power on self-test. If a component fails this check, you won't get a helpful visual error on the screen. Instead, you have to literally listen for diagnostic audio beep codes. For example, hearing one long and two short beeps can immediately isolate a video adapter failure. Identifying a pause issue tells you instantly that you are dealing with a pure hardware problem. All right, section 2, software, the digital brain. Moving one level up the tech stack, we arrive at the digital instructions that give all the physical hardware its actual purpose. It is absolutely vital to know whether you are troubleshooting system software or application software. System software is basically the master manager. It includes your operating system and your device drivers. Drivers act as translation manuals. They tell the OS exactly how to communicate with specific hardware components. Application software, on the other hand, relies entirely on that system software to function. These are the end-user programs you use every day, like web browsers and games. So if a game won't launch, that's an application issue. But if your OS can't talk to the graphics card at all, you're looking at a missing device driver, which is a system software issue. Digging a little deeper into system software, you've got to understand system architecture. This dictates how data is stored and how the CPU handles memory. Older 32-bit architecture, often called x86, is severely limited. It can really only utilize about 4 gigabytes of RAM. Modern 64-bit architecture, or x64, can address massive amounts of RAM. This terminology matters immediately in the real world. If a user is super frustrated because an install keeps failing, check the architecture. You simply cannot run a modern 64-bit application on an older 32-bit operating system. It just won't work. So how does modern computing scale all this up? Well, in enterprise environments, we don't always just run one operating system on one piece of physical hardware. Instead, specialized software called a hypervisor allocates resources to run multiple logical software-based virtual machines, or VMs, entirely within a single physical host. This kind of virtualization is literally the backbone of cloud computing, allowing data centers to host thousands of independent VMs on shared physical hardware. It's pretty amazing. Moving to section 3, communications connecting the world. Now that our machine is built and running, whether virtually or physically, we need the vocabulary to explain how it actually talks to everything else across the globe. We generally define networks by their physical distance, which is also known as their scope. A LAN, or local area network, connects devices within a single physical location, like a school or an office building. A WAN, or wide area network, connects multiple LANs over vast geographic distances. The internet itself is the world's largest one. Lastly, we have the PAN, or personal area network, which is very short range. Think of the Bluetooth connection between your smartphone and your wireless earbuds. For devices to actually find each other on those networks, they need addresses, and there are two you absolutely must know. First is the MAC address. This is a physical hardware address permanently burned into your network card. It never changes, making it a lot like a device's social security number. The IP address, however, is a logical network address that dynamically changes based on the specific network you're connected to. Think of the IP address like a device's current mailing address. It naturally changes when you pack up and move to a new location. Behind the scenes, networks operate using agreed-upon rules called protocols. Two of the most critical ones are DHCP and DNS. DHCP, or Dynamic Host Configuration Protocol, acts automatically to hand out those dynamic IP addresses the moment devices join the network. DNS, or Domain Name System, acts as the Internet's phone book. It translates human-readable words like professormesser.com into the machine routable IP addresses that computers actually use to find each other. To physically route all this traffic, we rely on specific networking hardware. We use a switch to connect local devices together on the exact same LAN, using their MAC addresses to forward data exactly where it needs to go. But to map paths across the broader internet, we use a router. A router connects different networks together from a LAN to WAN using IP addresses. Finally, we use wireless access points or WAPs to bridge wireless Wi-Fi clients into the wired network. Speaking of wireless, Wi-Fi operates on specific radio frequencies, and knowing the difference is a total game changer for troubleshooting. 2.4 gigahertz. Wi-Fi has excellent range and travels way better through walls, but it operates at slower speeds. 5 gigahertz Wi-Fi is much faster, but has a significantly shorter range. When you're diagnosing a complaint about slow internet, knowing these differences lets you troubleshoot based purely on the user's physical distance from the router. How cool is that? We really can't talk communications without touching on security, and precision here is critical for putting up the right defense. Malware is the overarching term for malicious software, which encompasses things like viruses and ransomware. Phishing is a specific deceptive social engineering attack, usually sent via email, aiming to trick users into revealing their credentials. And to secure your data while it's in transit over public untrusted networks, you use a VPN or virtual private network to establish a secure encrypted tunnel. By replacing guesswork and ambiguity with this standard IT terminology, you have laid the absolute perfect foundation to prepare for higher level computer courses like the CompTIA A+ certification. You've officially transformed from a standard computer user into a precision troubleshooter. So it leaves us with one incredibly exciting question. Now that you speak the language of tech, what will you build with it?
Let's see who turned in some work.